right, let's get started. All right, so today we'll just be talking about some recent applications. Again, nothing here will be covered in any of the homeworks or the exams, just the flavor of what types of stuff people are using machine learning for in the research that's been published in the last few years. And we'll start with a warm-up on using Lasso, which we covered a while back, on helping with things like cancer detection. And then we'll look at two more projects, one on personalization using Twitter, another on learning visual style that will use progressively more modern methods on progressively more interesting data sets. And so this lecture will be based on 3 papers that were published in the last several years. Okay, so first one, Lasso cancer detection. This is going to be a pretty quick one. The motivating application here was that when you, let's say in this case, the person has stomach cancer or gastric cancer, and the surgeon needs to basically cut away the portion of the tissue that is cancerous while leaving as much of the healthy tissue intact as possible, right? And so, the surgeon, this is how, at a high level, how it looks like right now. The surgeon removes tissue. The pathologist examines the tissue under a microscope. This could actually take a while, right? So it may take, some minutes, sometimes an hour. And then the pathologist determines if there's a margin, right? Is there a margin of healthy tissue that shows definitively that all the cancerous tissue was cut away? And if no margin, repeat step 1. Right? That's sort of the state-of-the-art best practice in medicine right now. Right. So what are some drawbacks of this approach? I think we can all think of lots of drawbacks, but I'll just highlight a few in particular. It's expensive, right? It requires an expert pathologist for every operation, and the pathologist, for the most part, just sit around dirtily doing nothing until he or she needs to check something, and then that's sort of not the most efficient use of their time, but that's sort of the protocol. It's slow. The examination can take quite a while, right? So up to an hour while the person is cut open, right? And unreliable, right? So sometimes, based off the microscope examination, you may not even be able to make a confident prediction. And so in that case, well, the default is to just cut more tissue, right? And so this is sort of the best practice that we have currently. And so, okay, well, why don't we try to use machine learning to think about if we can, make this process a bit more efficient. And we'll use Lasso. And Lasso, actually originated from the statistics community, so a lot of what will be presented right now will just basically be something that a statistician would, be very comfortable doing. And by the way, machine learning people love Lasso too, so we've more or less cannibalized it. And so, recall that this is the basic Lasso formulation, right? We have an L1 penalty on the weight vector or a parameter vector, and then we want to minimize some loss function I forgot to write loss, silly me, with respect to some function class parameterized by the weight vector, right? And so, okay, well, let's just train a model to predict the cancerous regions, right? So in this particular case, Y belongs to 3 classes, not 2. So there's cancerous, and then 2 forms of normal cells, epithelial and stromal. And we need to decide, well, what is the input feature vector? What does it look like? And what is the loss function? And where do we collect the training is also something that we need to think about as well, right? And so the feature vector is collected using mass spectrometry imaging. I don't know all the details of what's going on here. Basically, you shine some charged particles at some tissue, and then you look at some ion decay signatures, and that forms your X. And I'll give you a couple examples later on, or in the next slide. One of the nice things about this type of technology is that it effectively runs in real time. So you cut off the tissue, you put a sample in this contraption, and then within a second, you can get the readings that can form your X vector, right? And so the X vector is typically, you get a spectrum of decay signatures. So, things that discharge at certain parts of the spectrum, you're going to activate this, the feature value more highly. And for simplicity, we'll just have this tray of tissue, right? And we're going to discretize it into pixels, and we're going to compute this feature vector per pixel, and we'll predict, for simplicity, the class of tissue in each pixel independently. And so here are some of the visualizations of the feature vector at different values of the frequency, which then gets bucketed into this feature vector, right? So at different parts of the spectrum, you get different intensities for different parts of the tissue. Right? So this is the visualization. So essentially, each pixel has, in this case, 11,000 features, right, corresponding to discretizations of the spectrum. So that will form the basis of the feature vector. Any questions on that? Okay. So this is a 3-class problem. So we're going to do multi-class logistic regression in order to predict the class instead of binary logistic regression, or 2-class logistic regression. And it's a fairly straightforward generalization of binary logistic regression. Recall in binary logistic regression we had 2 y values, and I'll just use y equals plus or minus 1 just for this example. And this is the mathematical formula for logistic regression, right? And the key thing is that you want the probability to be proportional to this quantity, numerator. And that it gives you a straightforward generalization to multi-class logistic regression, where if we have k classes, where k is some number greater than 2, or it could even equal 2, then you want to be proportional to this quantity where this w, where we have k copies or k versions of this w vector, and k versions of the bias term, and each version corresponds to the weight vector for a specific class. Right? And then when we normalize by the total number of classes, which was 2 here, now it's some number greater than 2. And so this is multi-class regression. Everything else stays exactly the same. Gradient descent, it generalizes to this formulation in a very, very straightforward way. So there's nothing that's too complicated about this. Okay. Furthermore, we're going to impose a lasso penalty, right? So we're going to encourage the w vectors to be sparse by imposing a lasso penalty. 11,000 features is a lot of features. And the logistic regression loss is the negative log probability, right? So this is the loss function that we're going to minimize. And this, again, extends to the multi-class setting. All you do is plug in the ground truth, the correct y here, and then you just do greater than 7 on this term. Recall that W is actually a collection of feature vectors, right? K in particular. So this, I'm just abusing notation a little bit, but this L1 penalty basically corresponds to the sum of the absolute values of every entry of every weight vector for every class. That's the basic idea. Okay. So let's go back to the problem. So we're going to image the tissue samples. Each pixel in this image gives us a feature vector that is 11,000 features generated from mass spectrometry. This is computable in real time. And we're going to make one prediction, one multi-class prediction per pixel, right? And the way we collect ground truth in this case is, we can actually collect a data set where we can get more or less perfect results by putting it through to the lab, right? And this has a long turnaround time. You wouldn't want to do this while you're in an operation, right? Because it takes about 2 weeks, or at the time of this publication, it took about 2 weeks turnaround to get lab results. But certainly for collecting training data, right, where you really want the ground truth, this would be something that you'd want to do so that you don't need to have the supervision, right, at test time. Right? You because you could just predict on the x without having access to the y's at test time, which in this case would happen basically in real time. Any questions on that? Okay. So then we'll just learn a predictive model, right? So for this particular study, they collected a training set of 28 tissue samples from 14 patients. They did the standard cross-validation type of procedure. And then the test set is 21 tissue samples from 9 patients. The patients do not overlap with each other between training and test set. Right? And here are some performances. Let's see, how do we interpret this? So this is what's called a confusion matrix. We talked about this a little bit in one of the early lectures, where the rows correspond to the ground truth, and the columns correspond to the prediction. And if the prediction was perfect, only the diagonal entries would be non-zero, and anything on the off diagonal would be 0, right? We can also predict we don't know, right? And so we don't know just means, in this particular case, they decided that the logistic regression model needs to be at least 0.2, so 20% more confident in the highest prediction than the next highest prediction. So, if the highest prediction was cancer at 60% probability, or 50% probability, and the next highest was epithelial at 40% probability, then the model will predict, I don't know, because there's not a 20% margin. That's what that means. And so in general, the results are pretty good, right? You get something like 97, 96% agreement, right? If you just predict cancer versus normal, you get even higher agreement, right? And so this is something, at least on the surface, that seems like it could be promising enough to be useful in an actual operational setting, right? This is, of course, the data set is small, right? And so one shouldn't draw too many conclusions from this, but I think at the very least we can see that it's very promising. Any questions on that? Yes?
Is it being implemented now at all?
I suspect it will take a while. This isn't really a large enough data set to pass muster in the medical field. And furthermore, it requires a setup that may not be available in every hospital. And then there's the matter of lawsuits, right? So if this machine makes a misprediction and you cut away half the stomach when you could have only cut away a quarter of it, where's the liability? Is the liability in the machine with the machinery company? Is the liability with the hospital? So these are all issues that I think will work itself out over time. But these are the types of complications one has to deal with when thinking about actually applying these methods to these types of applications. Yes?
How's the overall agreement higher than any of the individual agreements?
How is the overall agreement higher than any of the individual agreements? You mean this guy?
Yeah. Am I misunderstanding?
There's maybe a case of Simpson's paradox. Let me think. Let me see here. This agreement is per row, right? This agreement is per row.
Yeah.
So if we do it instead by per column, I don't know for sure, but there are these paradoxes that happen depending on how you look at the data. either case, I absolve myself of all responsibility because it's not my paper. But I do think it's interesting. It's an interesting application. Okay, so recall that we actually used Lasso, right? So we wanted sparse models. In this case, the sparsity does tend to lead to a model that is, in some sense, relatively easy or feasible to interpret, right? And so here is we've shown a visualization. We've seen a visualization of the weight vector for the three classes, right? Epithelial, cancerous, and stromal. And so they're color coded. So positive means above the horizontal line means a large positive weight. Below means a large negative weight. And you could actually take this to a medical expert, and they can tell you, or an oncology expert, and they can tell you whether or not this type of model makes sense or not. Whether you're capturing something that's really in the data, or really believed to be crucial to the process of differentiating between these types of cells, or it's some spurious correlation that you really shouldn't trust. One thing that keep in mind is that in this type of X feature vector, there are many correlated features, right? So many features tend to be high or low in a very correlated way. And what Lasso will tend to do in such settings is it just picks one of those features and zeroes out the rest, right? And so if one of those features is the one you actually care about and it gets zeroed out, sometimes that can cause some confusion. And this is just some of the predictions, right? It's a tissue that's being imaged. Here's some of the heat maps of the different feature weights. This is the prediction, and this is the ground truth. Right? So it's pretty good. Okay, so this seems awesome. What's the catch? We already talked about some of the challenges. First of all, it's small sample size. 9 patients is not really that many, although the results are promising. Machine learning is only part of the solution. We need infrastructure, investment, agreement from the medical community. And there's, again, I alluded to this before, there are social, political, legal issues as well in these types of applications. If there's a misprediction, who's at fault? And we're already seeing this with self-driving cars, where some of the self-driving car technologies that are being deployed now, if there's an accident, who's at fault? Okay, any questions on this? Yes?
So I guess not on this, but on the previous one. Is there a way to impose additional penalties for, saying that something isn't cancer when it is cancer, as opposed to the other way around?
Yeah, so you could do cost-weighted mispredictions, but recall that in this particular case, the surgeons, they're not complete idiots. They're very good at their jobs. Most of the tissue they cut away, or a large fraction, in fact, if you look at the results, right, the largest proportion of the tissue that's cut is actually cancerous, right? So it forms the largest group, and if you just compare cancer versus non-cancer, it's about 50-50, right? And so you have to also keep in mind that these models are trained under the assumption that you're working with surgeons of this skill level, right? So that cost thing has to be balanced against how often what proportion they cut. So there's actually this process where if surgeons get better over time, right, and adapt to this type of technology in some way that's unexpected, you actually have to retrain the whole thing all over again because the distribution changes. Okay, so I'm going to move on to the next application, personalization via Twitter. This one will use some more of the concepts that we looked at in the last few lectures on representation learning. So this is the paper that I'll be discussing in this part of the lecture, representing documents to your readers. And so the motivation for this paper, as stated by the authors, was that it would be great to come up with smarter recommender systems that can help recommend articles of interest to us, the consumers of information, in a way that helps deal with the information overload. info, just one statistic that's actually quite outdated now. There are over 1 million news articles and blog posts generated every hour, right? And so, okay, how do we think about a news recommendation engine, right? So, we have a representation for the articles. We've talked about a number of representations. We have a user with some unknown preference vector, right? We recommend items to the user, and for simplicity, let's assume that the user either chooses to give an endorsement or withholds endorsement, right? So we have this data, this type of data, right? And then we want to learn something about the user preferences as a function of the representations of those documents, right? That's sort of the high-level idea, right? So one of the challenges that the authors of this paper sort of really thought about was, well, many common representations don't naturally line up with user interests, right? So you have very fine-grained representations such as bag of words. They tend to be too specific, right? So, if you look at this news article, a bag of words representation, if you sort of, it would give you something that looks like this. So this is a visualization of the bag of words feature vector, where size corresponds to magnitude. And it doesn't really tell you anything about topics, right? What we really care about are topics, right? On the other hand, we could do high-level topics from like a topic model, things related to things like PCA. And those can be too fuzzy or vague, right? They're really course-level topics, right? Like, for example, a topic could be a cluster, right? Now, if I have 10 clusters over millions of documents, each cluster is going to be very vague and diffuse, right? And so, and they could also be inconsistent over time, because what people talk about change over time, right? So, the word distribution of certain topics, it can drift a lot from day to day, week to week, depending on current events. Right? And so the goal then that the authors of this paper pursued was to improve recommendation performance through a more natural document representation, right? And so what they're going to leverage is the fact that news is social, right? So more people read a news through social media, through being exposed to social media rather than any other channel, right? And so, let's look at Twitter, right? So here is a fictitious Twitter handle, Substandard Nerd, and Substandard Nerd tweeted this article, right? So there's a few things going on here. Well, one, Substandard Nerd has a bunch of descriptors describing himself, and we can think of these as badges. So we're going to use that terminology, right? And we're going to think of Substandard Nerd tweeting this article as an endorsement of this article, okay? So, based off those ideas, let's learn a document representation based on how readers publicly describe themselves, right? So, for example, why is Substandard Nerd tweeting this article? Perhaps it is because this article speaks to the music badge, right? The music-loving badge for this person. That could be one sort of way of explaining why this article is being endorsed, right? And that's actually a very reasonable way of thinking about what's going on here in terms of a model of what's happening, right? So, using many tweets, can we learn that someone who identifies with music, right, and this is self-identified on the Twitter profiles, reads articles with these types of words, right? And this is the representation that we want to learn. Okay, so given a training set of tweeted articles for some specific time period, in this case the authors looked at about 3 million articles that were tweeted. The goal is to learn a representation of the training set, and what they call this a badge dictionary. So a badge dictionary is simply a matrix that is number of where every, I guess in this case, column is a badge, and every row is a word, right? So for example, the music badge would have this distribution over words. Right? And then we're going to use the badge dictionary to encode new articles, right? So, if we have this article, right, and we want to represent it as a linear combination over badges, and then that will give us this bag of words distribution, right, for this article. So at the end of the day, we still have a bag of words representation at the end of the day, but it has this low-dimensional bottleneck, which is badges, that creates this type of a bag of words representation rather than one that's super fine-grained over every word. Okay. So there's some advantages. This representation is very interpretable, right? So we have a label, if you will, for every dimension of our essentially a matrix factorization problem, because it's self-identified, and of course, therefore, it clearly corresponds to some specific set of user interests, right? It's at a higher level representation of words, right? If for this article, if this is the raw bag of words representation, if we compress it into badges and then reconstruct, if we compress this article into badge space and then reconstruct from badge space, we get this bag of words representation. And that's the idea. And another thing that's interesting is that if you actually train this model over multiple time periods, a Twitter user's badges, or how they self-identify, tends to be static over time. The word distribution of certain topics tend to drift over time because it's typically current events. And so, what is a politics badge might have a very different word representation from one time step to the next, and this actually can capture that because they all correspond to the same badge. And I'll sort of show a few examples of that later on in the lecture. And so, so given a training set of tweeted news articles and given a set of users with self-identified badges who tweeted these articles, we want to learn a badge dictionary from the training set. That's step one. And so this is a form of dictionary learning. Dictionary learning is a form of representation learning. And so there's the training data is the badges of the Twitter profile that tweeted this article, and a bag of words representation of this article, right? The raw bag of words representation. We normalize, so the authors chose to normalize. I think it helped with learning. And then this is, so that we have this Y for the bag of words representation, and we have the Z bag of badges representation for the user that tweeted the article, right? So in this case, there are actually potentially two badges that explain that can encode why this user tweeted this article. One is gig going and one is music love. And here's the training objective. It's one that I think we could all interpret very, very easily now. So we have a badge, the badge dictionary, and then the word representation, the encoding of the article as a function of the badges. And so we're going to impose an L1 penalty because we want these models to be sparse. And we want to minimize, in this case, a squared reconstruction error between the raw bag of words representation and a reconstruction of the bag of words as a function of a linear combination of badges. So the B is the badge dictionary, and the words are they correspond to a linear combination of the badges to form this, right? So B times W, I, gives you this. This is also known as an encoding. So the W gives you an encoding. The W gives you an encoding of the documents whose dimensionality is equal to the number of unique badges, which is much a lower number than the number of unique words, typically. Okay, this is a non-convex optimization problem. because of the multiplication here, non-convex. And the reason how you can tell that it's non-convex is, you know, you can, well, okay, it's easier to, okay, if you ignore these two terms, it's not convex even with these two terms, but if you ignore these two terms, I could rotate this guy and then anti-rotate this guy and you get the same answer. And so that type of symmetry will make it non-convex. In particular, if I initialize B and W to be 0, right? If B and W are initialized to be 0, there is no gradient. The gradient vanishes. You're at a saddle point. But it's clearly not an optimal solution. It is convex if we only optimize in B or W but not both. So it's convex if we hold one set of variables fixed. It becomes basically Lasso, right? Least squares regression with L1 regularization. But not if you optimize for both jointly, right? And so, you know, they do some alternating optimization. So one question is, okay, because it's not convex, initialization does matter. So how do we initialize this model in a way that we get nice solutions? Right? And so what the authors used is they used they simply used the average of the badges, right? So for this article, they initialized W as the average over all the active badges. The nice thing about this initialization is that if you know, for any given user, most of the badges will not be activated because you know, there's like 10,000 badges. Any given user might only have 10 or 20 that's active, and so this initialization says we're going to start by only looking at these badges that are active, and we're going to assume that none of the other badges can be used to encode this article. Okay, so you know, we have a problem here where, similar to the previous application, where, you know, badges occur in a correlated way, right? You know, if a user decides to self-identify with badge S, there's a higher probability that they'll self-identify with the badge T, right? And again, Lasso tends to focus on one of the correlated features and zeroes out the other one, even though both badges may be useful in describing or encoding the article, right? So, you know, let's look at Substandard Nerd again, right? There are a number of correlated badges here, Linux and Perl and hacking, those are correlated badges. You know, music, festival, gigs, those are also correlated badges. I have no idea how correlated cycling is to any of these. I suppose it is not, there's a non-trivial correlation there as well. Right. And so the solution is one that's fairly standard in the community. It's called graph-guided fuse lasso. And the basic idea is that, you know, although these lasso penalties, they tend to encourage the model to zero out all except one of the correlated features, right? This term says, okay, for badges that we know tend to co-occur, right? For badges that we know tend to co-occur, you can estimate this by just looking at pairwise co-occurrences on Twitter users. We're going to want their encodings to be similar, right? For any given document. And so this type of method is used in, you know, computational biology, in text, in lots of methods where you want sparsity, but you also want to make sure that you address, you know that you have lots of correlated features that you all want active, and so you want them to be, you don't want Lasso to zero all of them out completely if they're useful. Any questions on this? Yes.
How's this graph constructed?
Co-occurrence rates of badges on Twitter profiles.
So you have a node for every tag.
Yeah. So here, for example, if we look at all the users, Twitter users, we know that Linux and Perl co-occur a lot, right? And we want to learn a good encoding for both Linux and for Perl. And indeed, many articles can be coded using a combination of Linux and Perl. What Lasso will tend to do, because these two things are correlated, is they tend to just zero one of them out. And so what this big term will do is it'll just say, don't do that. We want these two to have similar magnitudes. Yeah. Okay. So now step 2, right? A badge is already learned, right? The badge dictionary is already learned. And now, given a new document, right, we want to learn a badge encoding of it, right? And so that simply boils down to this optimization problem. Oops. It's a fairly straightforward one. This is just a version of Lasso. This is just, so, because B is fixed. And that's sort of the recap of what's happening here, right? So the key difference between this type of approach and something like a generic latent factor model that we saw in lecture is that in a generic latent factor model, we had no control over what the dimensions of the latent representation meant, right? Whereas here we do, because we initialized the representation rather than randomly. If we initialize this thing randomly, it would just be a standard latent factor model, right? If we initialize this randomly, it would just be a standard latent factor model. The thing that gives this thing, the thing that really sort of we're exploiting in this whole thing, that makes each of the dimensions in the latent representation meaningful, is the fact that we initialize in this way using the badges. And so here are some examples. This is from a few years ago. This is during the 2012 presidential election cycle. And so these are some of the if you look at the latent dimensions corresponding to these badges, this is sort of the words that are active in those badges, right? And so you can think of these as sort of visualizing the columns of view in the latent factor model. Now, one thing that's interesting is that we could run this model over multiple time frames, right? Because the user's badges, they don't change typically, right? So we could run this model over multiple time frames. So in September 2012, this was the encoding of the badges, right? Or excuse me, this was the representation for the model. And then in September 2010, 2 years earlier, this was the model, right? For the same badge. So now we can represent, concepts as a function of badges, and the meaning of badges can drift, at least in terms of the low-level word representation, can drift along with whatever is of contemporary interest in the news cycle. Yes.
How did, or maybe I missed the point, but did the authors do anything to try to ensure that they were, particularly for like political terms, like collecting articles from a wide range of sources? Was that any actual training?
I think a lot of the articles that get tweeted are political. Yeah. But not all, certainly.
But I mean, like, did they do anything to ensure that, like, I mean, of course, all the articles that are tweeted are political. Did they do anything to ensure that, like, they ran the gamut of the political spectrum?
Oh, they definitely did. Yeah, they definitely did. Yeah.
Okay.
Twitter is it's a wild world out there. It's a crazy world out there. So here's one example. We could look at just people who are political pundits, right? So there's two badges. One is called progressive, and one is called TCOT, which stands for top conservatives on Twitter. And using this encoding, right, we can, predict the political alignments of likely readers, right? So, you can actually, if you project people onto this two-dimensional thing, right, then you get this, right? You get Ann Coulter as very conservative. You get Paul Krugman as very liberal, and so on and so forth. Yeah. And so another thing that one of the ultimate tests of these representation learning problems is, okay, they look nice, you can sort of interpret parts of it. Everyone does this. Every paper you'll see that gets published these days on representation learning has some nice visualizations of the representations. Is it useful? Right? And so one way to sort of address this question is to do a user study, right? So one of the motivations for doing this project, as stated by the authors, was that we want to have a better representation for capturing user preferences, right? What's a good way to represent what users are interested in? Right? What's a good representation for that? And so, we could run a user study where we ask people to rate a few articles, right? And then we pick a representation. So this is a user study where we pick a baseline representation or this representation, right? So there's a number of representations, and then we learn a user preference vector using this representation of the articles that the user said that they liked, and then go to the next time period and then do this again, right? Recommend according to these preferences, and then see if we get more of them right, right? And so here's a result. Higher is better, right, in time step 2, and you can see that using this badge representation, we do get a lift in the number of liked articles for the user. Right. So just to recap, this was an application of sparse dictionary learning, right, where we want to learn a new representation of articles that's useful for capturing user preferences. And then encode these articles using this representation, and the new twist is that this representation uses social data as a way to do a smart initialization of the latent factor modeling, so that each dimension of this latent representation is actually very meaningful, can drift over time, in fact, in a semantically coherent way, and can be used as a low-dimensional representation to capture user interests that stay persistent over time, even if the specific low-level topics change with current events. Any questions on that? All right. The last one I'll talk about is a project on learning visual style. So the paper I'll be describing is learning visual clothing style with heterogeneous dyadic co-occurrences. Excuse me. And so here's one of the sort of the motivating applications, right? So we want a model that can say something like, well, this type of outfit you see on the left, there's in some sense compatible. And then these types of outfits you see on the right are in some sense incompatible. That's sort of the thing that you want to learn. The training data comes from some very laborious and painstaking scraping of Amazon. There's a funny backstory there, but I don't think I should tell it on camera. So you have a ground set of items, about 1 million. You have the image of every item, and then you have the category of that item, like coat, belt, pants, socks, etc. You can also extract some pairwise relationships, like on Amazon, when you look at an item, you can also extract this item was also bought with this other item, or people who looked at this item also looked at this other item, right? So those are types of relationships. Those are types of metadata you can actually scrape off of Amazon. At least you used to be able to. So So here's one way to formulate the learning objective, right? Again, one of the goals here is to learn a useful representation. So we have a loss function, so capital theta corresponds to all model parameters. And we're going to learn a representation, and I'll call this an embedding here, just to sort of prime sort of the semantics of this representation of images, right? And so the left summation sums over all compatible pairs as extracted from metadata on Amazon. Like these two items are frequently purchased together. And this loss function penalizes if these embeddings are too far from each other, right? So if the embedding representation for these two images are too far from each other in the embedding space, then this loss function will be large. Okay? And this, the right summation sums over all incompatible pairs, right? And this loss function will be high if the embeddings for these two items that are incompatible are too close to each other, right? And we're only going to look at pairs of items in different categories. So, you know, shoes and socks, pants and shirts, etc. Right? One thing to keep in mind is that we don't actually have explicit information of what is incompatible. We only have explicit information of what is compatible, right? And so what the authors did was they just simply assumed that anything that wasn't explicitly compatible was probably incompatible, and they just subsampled a subset of that, right? The number of incompatible things is much larger than the number of compatible things under that assumption. So they just subsampled a number of those, and then they populated this summation. And this actually is an issue that is often happens in these types of data sets, where the absence of an endorsement does not mean necessarily that it's a negative feedback. It just means lack of positive feedback. And one thing that many people often do is that they just consider the absence of positive feedback to be weak negative feedback. And that's essentially what's going on. Any questions? Yes?
Can you go back to the pictures for a second? For visually incompatible, are they all pairwise incompatible with each other?
Yeah, you know, I don't actually know. I think. Let me look. I think it's the rows that are compatible or incompatible. Right. So this row. So these three items are incompatible with these three items. But these are gym socks. These are, and whereas these three items are compatible with these items. Yeah.
Okay, that makes more sense.
Yeah. Okay, so the embedding will be learned using a variant of convolutional neural nets. We talked about this a while back, I guess. And so the thing that's going to happen is that, you know, in normal convolutional neural nets, for example, for ImageNet or for MNIST, we do some sort of, let's say, logistic regression at the top layer where we predict a one of k categories. All we're going to do is we're not going to do that, right? We're just going to, we're not going to do some supervised prediction like that at the top layer. We're going to throw the top layer away, right? And we're going to use the, you know, let's say in this specific case, the next highest layer. We're going to use that as the embedding, right? In this case, it's 4096. Probably is too many, but, you know, just for illustrative purposes, that's sort of the idea. So that is the embedding. We're going to learn this feature vector for images that minimizes the aforementioned loss function. And this feature vector is the way we convert from images to this feature vector is through a convolutional neural network whose parameters we'll learn. That's the capital theta from the previous slide. Right. And so the method they produced, it's a cute name. It's called Siamese convolutional neural networks. Right. So you have a pair of images, xi and xj. So you think of these as images, right? We push those through a CNN, right? And we get out an embedding. So this is the second to last layer of a traditional CNN. We've thrown away the last output layer. right? And then we have a loss function that says if these two embeddings should be closer together or further apart, right? And that propagates a gradient, that backprops a gradient through this whole convolutional neural net whose parameters we're trying to optimize. And the reason it's called Siamese is because these two neural nets are actually the same neural net, right? Yeah, they're joined at something. So they're the exact same neural net. So whatever gradient goes through here will affect the parameters of here. Right? That's the basic idea. Right, it's the same model. So here is the overall idea, right? So we have this embedding over images, capital Phi, and capital Phi is parameterized by theta. So I'm not using all the notation here just because it'll get too busy. But you can think of capital Phi as a convolutional neural net that returns, some k-dimensional embedding, and all the parameters of the convolutional neural net is capital theta. And we want to learn this, and this is the same Phi function. So for these images, we want to learn embedding where we'll learn a neural net embedded where the embedding is close together, and over here we want to learn it where it's further apart. We train the whole thing using gradient descent or stochastic gradient descent, and so that's basically it. I'm not going to go through the details of these two loss functions. I think if you look at the paper, the authors tried a few different choices, and they're all the ones that you would normally think about trying. Right, so you want the embedding to be small. You don't actually want to learn a 4096 embedding, dimensional embedding. So the authors used 128 for the top layer. And again, we did a subsample negative pairs. Right. Any questions on that? Yes?
Why not just downweight the negative component instead of subsample?
There's a computational cost there, right? If there's like 100 million items on Amazon, that's 100 million squared, right? Because most items are not bought, purchased here. Yeah. So it typically in practice it makes almost no difference, and it's computationally a lot more convenient. Okay, so let's look at some of the visualizations. So they visualize a 2D projection of this embedding, right? So they took a bunch of images from the Amazon items, and they learned their embeddings using this learning algorithm. And then they took the embedding, they projected onto 2D just for visualization purposes, and then you could sort of zoom in on different parts of this embedding space to see what kind of images come out of there. And so over here you have casual clothing, over here we have gym wear, so on and so forth. Children's clothes. So, visualizations, again, are nice. Every representation learning paper has one, including several of mine. But again, the question is, well, is it useful, right? And so here's one thing that they tried to show that the recommendations made with this are actually pretty useful, are pretty interesting. And so given one item, right? And here they use the categories upper, lower, and footwear. Can we sort of use this embedding to recommend items in these categories that don't appear in the Amazon frequently bought together thing, right? So we can sort of fill in missing data, if you will. And so here's one prediction that they made, right? So this triplet does not appear in the Amazon frequently purchased together, but you can sort of fill in these missing values using this approach. Here's another one. This guy. It's not perfect, but you know, I think it's actually pretty interesting. And with more data, you know, you could probably do better. Okay, wait, sorry, any questions on this? Okay, so, you know, sorry. One of the challenges is that, you know, this approach is not robust to label-wise, right? You know, for example, if this pair of pants is miscategorized as shoes, which does happen in the Amazon data set. Well, that's actually going to be the closest embedding point, right? Because the neural net will project those things, well, two pairs of genes to very similar locations in the embedding space. And so if you just did a naive find the closest pants, or find the closest shoes to these pants in the embedding space and recommend that, you're gonna recommend pants as shoes because of the label miscategorization, right? So of course, you know, miscategorization are rare, but in this particular case, they're the ones that always get picked if you don't consider them, right? So instead of predicting the closest shoe, let's predict the closest cluster of shoes, right? So with the idea being that, you know, if pants were miscategorized as shoes, then if we look at the embedding overall shoes, this pants will be sort of very far away from large clusters of shoes in the embedding. So we'll cluster every category. And given an input query, find the closest cluster center of some other category to match with the input query. That's the idea. And that's how you get the robust categorization recommendation that doesn't sort of give you these weird outlier recommendations. We can also use this embedding space to compute things like coherence, right, or coordination, right? If you pick a set of outfits and they're all really close to each other in the embedding space, you can say that that's a coordinated outfit. If you pick a set of outfits whose individual items are far apart in the embedding space, you can say, well, okay, that's probably less coordinated. Right? Again, it's not perfect, but I think it's kind of interesting. One can also look at temporal, right? So here, this is the embedding, and at the bottom, you get this heat map of activity of purchases. I think it's purchases. I forget if it's purchases or searches. Of activity, you know, depending on the time of over a period of about 10 years. So you can actually use this to analyze trends, right? So in particular, I think here they're looking at shoes, right? And so these type of shoes, you know, start out, become really hot around this time, and then by about 2014, they're no longer very popular. Right? Any questions on that? Okay, so just to recap, so we looked at two concepts today. So first we started thinking about how sparsity is useful in practice, right? It gives us interpretability in you know, along a certain dimension, and we learned it using typically an L1 objective, or Lasso, extensions of Lasso. And then we spent a long time looking at how representations can be useful. And usefulness of representation learning is always a kind of a fuzzy thing to sort of nail down because it's not supervised learning, right? We don't have some like gold standard objective to quantify how well we're doing. So you have to sort of try to see if it can be useful in a variety of different ways, such as recommender systems, analyzing trends, and stuff like that. That essentially boils down to learning this low-dimensional encoding or embedding of raw data in a way that reflects what you want to use it for, and it's hopefully this low-dimensional embedding is better suited to interpreting the semantics of this particular data domain. And so this will conclude the portion of the course on representation learning. Are there any questions about that in general? Okay, great. Next week we'll look at probabilistic models. That's it.